It seems like everywhere you turn, everyone's buzzing about these, massive language models,
Yeah.
LLMs. It's all very exciting. But honestly, sometimes I just wonder, how sustainable is this whole arms race to build bigger and bigger models?
Yeah, I get that.
The sheer size and
Yeah.
cost of training these things
Mhm.
feels like it's creating a real divide in, well, who actually gets to play in this advanced AI space?
I think that's the core issue that this report really tries to address. You're absolutely right. The absolute cutting edge of AI, especially with these huge models, it risks becoming this like exclusive club because of the incredible resources you need just to build them.
Yeah. And that's actually a perfect segue into our deep dive today. We're looking at this technical report. Every flop counts. Scaling a 300B mixture of experts, Ling LMM, without premium GPUs. I mean, even the title kind of hints at the central challenge here, doesn't it?
It really does. The researchers at AI at Ant Group, they were very focused on how to make this, more accessible. So it wasn't just about how do we make bigger models. It was how do we be much smarter about the way we scale, especially when we don't all have access to the top of the line GPUs like your H100s and H800s, which is a lot of times financially prohibitive.
Right. So who are the key players here? We're talking about the Ling models.
Exactly. So they developed two main types of what are called mixture of experts models, MoE. You have Ling-Lite, which is 16.8 billion parameters, but the clever bit is that only about 2.75 billion of those are actually activated for any given input. So it's like having, a massive team of specialists, but only the most relevant experts are called upon for each specific problem.
Interesting. So it's a more efficient approach, basically.
Yeah, much more focused. And then, of course, they scale that up. So you have Ling-Plus, also sometimes called Bailing, which roughly translates to 100 billion. This one's significantly larger, 290 billion parameters. And of those, about 28.8 billion activated. And what's really striking is even without relying solely on the absolute best and most expensive hardware, they were able to achieve performance that is really right up there with the leading industry benchmarks.
So that's the big headline here. You don't need a supercomputer's worth of the latest GPUs to get these, top tier results. So for our listener, what's the mission of our deep dive today?
I think the goal is to really understand what were the methods that they used to train these MoE LLMs so efficiently, and how can we apply those to make AI development more accessible, especially when resources are constrained. And so we'll be focusing on how they effectively train a 300 billion parameter model on less powerful hardware, all while hitting those high performance marks and even keeping the computing costs significantly lower.
Okay, let's dive into that. So the report starts by kind of outlining this fundamental problem, right? Which is this sort of limitation of resources.
Yeah.
And it's not just about, wanting the shiniest new tech. There are real world implications for our listeners in terms of economics and accessibility.
Absolutely. I mean, the researchers make it very clear that the cost and the availability of these high performance AI accelerators, the H100s and the H200s that we just mentioned, they create a pretty significant barrier. It prevents a much wider community of researchers and organizations from even being able to train these incredibly large and capable MoE models.
It makes me think about that point that DeepSeek made about the day-night inference load, right?
Yeah.
Where everyone needs those top-tier resources at the same time, and it creates this bottleneck.
Yeah, that's a really good analogy. And just like during that peak usage for AI services, for training these models, the demand for these top tier resources is really high, which leads to those, ongoing shortages.
Right. But as the report highlights, there's this whole range of, slightly less glamorous but still very capable hardware out there,
Yeah.
and potentially much more cost effective.
Exactly. So you can find these lower performance accelerators in much greater abundance, and oftentimes they can offer a significant cost advantage per unit of compute. So the real core question that they were trying to answer is how do you train these advanced models, like your MoE architectures, when you can't always count on having that perfectly optimized environment of a top tier system?
So that brings us to the real technical challenges that they had to overcome. What were those major hurdles?
So they really identify three main technical challenges. The first is what they call cross-cluster, cross-device compatibility. And what they mean by this is that different hardware setups, whether it's different kinds of AI chips or even different groups of machines working together, they often have inconsistencies. This could be in how they handle basic calculations, how they handle communication between the devices, or even just the software frameworks that are used for distributed training.
So it's not as simple as just plugging everything in and hitting go.
Right, especially not with these MoE models, because MoE architectures rely on some very specific types of calculations, things like group gem and permute, unpermute, and all-to-all operations, and those are really essential for efficient communication between the different expert parts of the model. And then you have distributed training methods like expert parallelism, where different experts might be on different machines, and these might be completely absent, or they might work differently on different hardware or cluster configurations. So really, ensuring that your model trains accurately and that you can even move your training between different setups becomes a significant technical hurdle.
Right, right. Okay, so what was the second major challenge?
So the second one they really highlight is the reliability of cross-cluster resource synchronization. And when you're working with these, extremely large MoE models, the data sets and even just the checkpoints, the intermediate saved states of your model training, they can grow to, petabyte scale.
Wow.
And so moving these things between different clusters, it requires really seamless and really fast synchronization of all of that data.
Yeah, I mean, petabytes that's almost incomprehensible. And if that synchronization breaks down, I imagine your whole training process could be, at risk.
Exactly. So that was a key challenge for them to solve. And then the final one that they identified is what they call cost performance optimization. And it's not just about getting the model to train, it's about doing it in a way that really balances the cost of those computing resources with the final performance of the model that you achieve. So it really involves figuring out how to allocate your hardware, how to schedule your jobs, and how to make those smart trade-offs between how fast you can compute versus the precision of your calculations, and really, even designing and scaling that model architecture itself to get the most performance for your investment.
Gotcha. So we've defined the challenges. How did they actually tackle them? What were the key optimization strategies?
So they really implemented a whole set of optimization strategies, everything from the model architecture itself to the training process, how they handle errors, and even how they evaluated those final models.
Right. Let's start with the core of it all,
Mm-hmm.
the model architecture and the training approach.
Okay, so they really highlight the importance of first picking the right model architecture, one that's actually suited to the resources that you have available. And this really ties into the idea of scaling laws, understanding how, model size and the amount of data and the compute power all kind of interact. And then from there, they introduce what they call DL Rover.
DL Rover. Okay.
Yeah. And this is their open source, unified distributed deep learning framework. So you can kind of think of it as this central platform that can work with all these various other training frameworks, and that allows them to run on these different heterogeneous computing setups that we were just talking about.
So it's like a universal adapter for different AI training systems.
Yeah, that's a good way to think about it.
Nice.
And then to really understand what's happening under the hood on these diverse platforms, they developed something called XPUTimer. Yeah. And this is really a lightweight debugging tool that's designed to analyze how tasks perform on different computing environments. And remarkably, they report that this tool can actually reduce the memory usage by something like 90% compared to traditional methods.
A 90% reduction in memory usage for debugging. That's a huge efficiency gain.
It is.
Okay.
And then they move on to something they call EDIT Elastic Distributed Training. And this is their platform agnostic asynchronous training strategy.
Asynchronous meaning like things don't have to happen in perfect lockstep on all the machines.
Exactly. And in traditional synchronous training, all parts of your distributed system have to kind of wait for the slowest one to finish before you can move on to the next step. And that can be really inefficient, especially if you have, slower machines, sometimes called stragglers.
Yeah.
So what EDIT does is it uses this idea of layer-wise synchronization, where you synchronize the model parameters layer by layer, and time-based synchronization, where faster nodes can actually perform more local updates before they have to sync up. And this really helps to reduce the impact of those slower machines. And they report that this can actually reduce the training time by as much as 66.1% in some of their setups.
That's massive. So it's kind of like letting the faster runners in a race get ahead instead of making everyone wait at each checkpoint.
Exactly.
Okay, cool.
And then, they go beyond just those model model and training level optimizations. They even look at how the data itself is stored and accessed. So they employ techniques like device multi-tenancy, and they use FuseS, which is a way to create custom file systems. And what this does is it helps them achieve high performance and also makes their storage system more adaptable across multiple clusters. And so they say by carefully considering how that storage and training process kind of interacts, they manage to reduce the I/O overhead, the time spent reading and writing data by about 50% in MoE training scenarios.
Nice. So they've optimized the model, the training infrastructure. What about when things inevitably go wrong? Because I'm sure with systems this complex, errors are bound to pop up.
Absolutely. And so to refine the way they handle those training errors, those anomalies, they develop a pretty sophisticated system. So this includes a multi-level anomaly detection system that monitors the training process kind of in real time, and it can flag those potential problems. And if something does go wrong, they actually have an automated checkpoint recovery mechanism. So if there's a hardware failure or, one of those problematic loss anomalies, like a sudden spike or drop in the training loss, they can recover from that and minimize the impact.
So it's kind of like a safety net, so you don't lose, weeks of training to a minor glitch.
Exactly. Then they move on to making the model evaluation more efficient. And this is really, crucial for understanding how well your training is progressing, especially when you're training across multiple clusters.
So how do they improve that evaluation process?
So they did a few things. First of all, they created domain-specific evaluation data sets, and they really optimized their prediction and prompting strategies. And this was partly to address situations where the model might initially underperform. It was also to improve the consistency of those evaluation results. And they also developed something called Flood.
Flood, yeah?
Yeah. And this is their scalable offline inference framework. It's designed to provide very consistent evaluation results, even when you're running across different clusters. And they claim an average deviation of less than 0.5%, which is incredibly consistent. And then to top it off, they have this automated analysis system that can actually link the evaluation results back to the model's performance and the training data sets. So that gives them kind of real-time feedback and helps them fine-tune those training strategies.
So it's a closed loop. You train, you evaluate efficiently and consistently, you analyze the results, and you feed that back into the process, right?
Exactly.
Perfect. Makes sense. Now, the report also talks about enhancing the model's ability to use tools. And that's an increasingly important aspect of this, more advanced AI.
It is. And it seems like the Ling models are actually quite skilled at it. And they focused on two main things here. First is high-quality data synthesis. And so they use knowledge graph technology and what they call generalized calling instructions to actually generate a large set of this tool-used data. And this data includes, complex sequences of these function calls, and it helps the models learn how to really interact with all these different tools out in the real world.
So it's like you're not just teaching the model how to use a hammer, for example. You're teaching it the concept of, tools and construction and how all these things work together.
Yeah, exactly. And then second, they implemented what they call adaptive tool learning strategies. And so this involves things like rejection sampling, where the model tries different ways of using the tool and kind of learns from its mistakes. And then error correction through what they call self-reflective multi-agent interactive dialogues. So it's almost as if the model can have a conversation with itself or even with, other AI agents to figure out the best way to use the tool and recover from those errors.
That's cool. So it sounds like they built this, really comprehensive system, not just for training the model, but for making it practical and, useful and highly capable.
Absolutely. And so all of these optimizations culminated in, the development and the training of their Ling models. And they give some really interesting details about Ling-Plus in action.
So give it to me. How did all this translate into, tangible results?
So they pre-trained Ling-Plus on a massive 9 trillion tokens. And this was actually done across 5 different hardware configurations, which they detail in their table. And what's really significant is the comparison they make. So they estimate that training 1 trillion tokens on what they call device D, their high-performance hardware setup would cost about 6.35 million RMB. But by using a lower specification hardware system, that cost dropped to about 5.08 8 million RMB.
That's a pretty significant saving, right? Almost 20% reduction in, computing cost. For a smaller company, that could be a game changer.
Absolutely. And then the evaluation results, I think, really speak for themselves. They tested the Lin models on all these different industry standard benchmarks. And what they found is that, with similar parameter sizes, their models trained under these more resource efficient conditions achieved performance that was directly comparable to the leading open source models. And they particularly excelled at tool use, which they illustrate in a couple of their figures.
So every flop counts really paid off.
It did.
They got top-tier performance without relying on top-tier hardware and saved a ton of money in the process.
Exactly.
That's a really clear path for others to follow, I think.
Absolutely. And then they also go into some of the architectural innovations that they immigrated into the Ling models themselves.
Okay.
So going beyond just the training strategies.
So what makes the Ling architecture stand out?
Well, one of the key things is their use of what they call fine-grained experts within that MoE architecture. And so instead of having a smaller number of very large experts, they actually increase the number of experts while they proportionally decrease the size of each individual expert. And so the idea here is to really create this much higher degree of specialization across a broader range of knowledge.
It's like having a much larger and more diverse team, but each member has a very, very specific area of expertise.
Exactly. But then they realize that relying solely on these fine-grained experts, it might make it harder for those individual experts to develop, both general capabilities and more specialized ones. So they introduce this idea of a share expert.
Okay.
And this is an additional expert that can process all tokens regardless of how they're routed. And this really ensures that the model maintains a kind of strong foundation of general knowledge alongside the specialized knowledge of all those other experts.
It's like having a generalist on the team to make sure everyone's kind of on the same page.
Exactly. And then when it comes to actually directing those tokens to the experts, they use this dropless routing strategy. And so this ensures that all of the training data is being utilized effectively. And then to kind of maintain that balance among the experts, they have these two mechanisms, what they call load balance loss and router Z loss. And these help to improve the training efficiency and prevent situations where some experts might be heavily used while others are sitting idle.
So load balancing is crucial in any kind of distributed system. What other architectural things did they do?
So another one they highlight is this problem of training instability, especially in those early stages of pre-training. And so they use a technique called stochastic routing warm-up. And so what this does is instead of just immediately relying on that learned routing mechanism to decide which expert gets which data, they actually inject some randomness into it during that early phase. And this helps prevent any single expert from becoming kind of overloaded and causing instability. And then that randomness is gradually decreased as training progresses.
So it's kind of like easing the model into its specialized behavior.
Exactly. And then finally, they implement what they call norm head, which is their normed LM head. And so they observed that the output scale of that language modeling head could become unstable during training, especially during some of those loss spikes. And so by applying L2 normalization to the weights of that LM head before token prediction, they ensure that those variations in weight magnitude don't contribute to that instability.
Gotcha. So it's a lot of these very thoughtful adjustments to improve, efficiency, stability, performance, especially when you're working with more limited resources.
Exactly.
Now, going back to that discussion about scaling laws, they also did this pretty interesting systematic analysis of how the MoE architecture scales with respect to batch size and learning rate, right?
They did.
And so did they find that MoE models follow the same fundamental principles as dense models when it comes to these key training parameters?
So interestingly, their findings indicate that the scaling behaviors of both batch size and learning rate for MoE models actually do align with those observed in dense models. And so essentially for a given computational budget, the optimal values for those hyperparameters are primarily determined by the total amount of computation, not so much by the specific MoE architecture or those auxiliary loss functions that they use.
So the basic rules of scaling still apply, even with the added complexity of, this MoE structure.
Exactly.
Okay, that makes it easier to predict and optimize training.
Yeah. But what's even more compelling is that when they look at the model performance scaling, they directly compare the MoE and dense architectures under the same computational budget. And they consistently find that the MoE architecture achieves a significantly lower training loss.
How much more efficient were they?
So on average, they calculate an efficiency advantage of about 3 times.
Wow.
So that means the MoE architecture was roughly 3 times more computationally efficient than a dense architecture to reach the same level of training loss.
That's a pretty significant efficiency gain.
It is. And it seemed like that advantage actually grew with larger computational budgets, suggesting that, the MoE models become even more beneficial at those very large scales.
That's interesting. So that really highlights, the power of MoE for large-scale AI.
Hmm.
And the report goes on to kind of give some key highlights from both the pre-training phase and the post-training alignment, right?
Right.
So let's talk about the pre-training recipe. What were the main ingredients in the process there?
So for their initial pre-training for Ling-Plus, they used the Atom W optimizer with a carefully chosen set of hyperparameters. So they use a learning rate schedule that includes this warm-up period followed by stable decay, and they peak at a learning rate of 2.44. They also implement a batch size warm-up strategy, starting with a smaller batch size and gradually increasing it. Gradient clipping is set to 1.0. Maximum sequence length was initially 4K tokens. They trained on a massive 9 trillion tokens during this initial stage, and they did not actually use any token dropping techniques.
Wow, that's a lot of data.
It is. And then, throughout the training, they were monitoring these various metrics, and they even make adjustments to their pre-training data mix, increasing the proportion of high-quality data and using things like online data deduplication to make sure that the data remains unique and relevant.
Gotcha.
And then they move on to this long context pre-training stage, so focusing on the model's ability to process these longer sequences of text.
Right, that's becoming more and more important these days. So how did they adjust their training for that?
So they extend the maximum input sequence length all the way up to 16K tokens using rotary position embedding with some adjusted parameters. And you can kind of think of ROPE as a way for the model to understand the position of words in a very long sequence. And they also modify their training data set to better suit long context processing. So
Right.
for example, they reduce the amount of web-derived data and they incorporate more long-form text. And they continue training for another 150 billion tokens. And they report that as a result, Ling-Plus achieved near perfect performance on what's called needle in a haystack testing across context lengths up to 64K.
So pretty impressive recall for, information that's deep down in these texts.
It is. And then the final phase of the pre-training was what they call an annealing stage. And here they systematically reduce the learning rate using this inverse square root decay schedule. And they do this exclusively on their highest quality curated data sets. And then they also implement these mechanisms to deal with those disruptive loss spikes that can happen during training.
So loss spikes, those sudden increases in the training loss that can really mess things up.
Exactly.
How do they deal with those?
So they implement these skip and retry mechanisms. So if a loss spike happens during a training update, that update is skipped, the current state of the model is saved, and then they try that update again. And if the spike persists even after the retry, they'll automatically reduce the learning rate just for that training step.
Okay, so it's a way to manage those, inevitable hiccups.
Yeah.
Now, after all this extensive pre-training, there's still the really crucial step of aligning the model to be more helpful and harmless and, useful in general.
Right. So their post-training alignment involved a two-stage process: supervised fine-tuning, SFT, and then direct preference optimization, DPO. And this was actually kind of an iterative process where the best model from each cycle was then used to refine both the training data and the model itself for the next phase.
Right. So let's start with the supervised fine-tuning. What kind of data did they use to guide the model in this stage?
So they started with a seed data set of about 1 to 2 million examples. This included both, human annotated data and publicly available open source data. But then they significantly expanded this data set using data synthesis techniques.
Right.
Because as, human generated data becomes increasingly scarce and expensive to annotate, synthetic data really plays this crucial role.
So how did they make sure this synthetic data was actually good?
So they use these methodologies inspired by existing approaches to generate kind of these novel and diverse problem prompts. And then they use rejection sampling to actually generate multiple candidate responses for each prompt. And then they have this whole pipeline for selecting the best ones. And they specifically tailor this for reasoning-based data. So things like, code, math, logic, and then non-reasoning data.
What kind of quality control measures did they have in place?
So for the reasoning data, they implement a series of rule-based filtering mechanisms. So for code, this involved things like, validation through checks and actually running tests, generating test cases to really verify that the code is correct. For math, they would actually prompt LLMs to kind of translate the computational logic into code that they could then execute to check the answers. And then for logical reasoning, they use this majority voting system among the multiple generated solutions. And they found that these methods were very effective in eliminating a lot of those incorrect responses. And then for both the filtered reasoning data and the non-reasoning data, they use an LLM-based judge to further assess the relevance and the quality of the generated content.
So to take care of quality. What about repetition? I mean, there's a lot of, overlap in the synthetic data.
Yeah, absolutely. They encountered this problem of redundancy, especially in the code-related synthetic data. And so to address that, they implemented this semantic-based deduplication method. So what they do is they use a high-performing text embedding model to map both the prompts and the generated responses into a vector space. And then they remove data points that have this high degree of cosine similarity.
Okay.
So this effectively reduces redundancy without negatively impacting the model's core capabilities.
Nice. So after that very thorough SFT,
Mhm.
they move on to direct preference optimization. What was the goal there?
So the DPO has two primary phases. The first is what they call vanilla DPO or VD. And here the main goal is to really enhance the model's authenticity, its relevance, its harmlessness, and its ability to follow, those more complex instructions. And then the second phase is what they call robustness optimization or RO. And this is designed to strengthen the model's stability and the consistency of its reasoning across, a wider range of tasks.
And you said they also improved the efficiency of the DPO process.
Yeah, so they implemented this data packing strategy, and this involved padding both the chosen and the rejected sequences to that maximum sequence length that was used during training. And this seemingly simple optimization actually resulted in a significant 3.7-fold increase in the speed of that DPO training.
Okay. So they tried a few other things, but that was the one that worked.
Yeah. They also tried length regularized DPO and avoiding those repeated prompts, but they didn't see any significant performance improvements there.
Now, given all this focus on long context abilities, how did they specifically tailor that post-training for those, longer inputs?
So for long context post-training, they employed several strategies. So they synthesized long context instruction data. They did this by basically concatenating multiple high-quality documents and then prompting the model with various tasks that required, understanding that the entire context. And to specifically address this issue of lost in the middle, where models sometimes struggle to access information in the middle of very long documents, they created these specialized data sets where they actually deliberately insert crucial information in the middle of those passages.
So they're trying to break the model.
Yeah, in a way. And they also use a progressive fine-tuning strategy. So first, they adapt the model to shorter context data, and then they gradually introduce longer context data. And they use a specific ratio to kind of balance the performance across the different input lengths.
Gotcha.
And then finally, for tool use, they specifically trained the models to really interact effectively with public APIs, with application-specific APIs, and even synthetic APIs. And so their approach really focused on the synthesis of high-quality tool use data.
Right.
And that involves things like carefully collecting tool instructions, generalizing task planning, and even using the Ling models themselves as policy agents to decide which tool to use.
So it sounds like they've really covered every stage of development, from pre-training to really nuanced post-training alignment and specific tool use enhancements.
They really have.
So how do they actually perform when put to the test?
So for evaluation, they use a comprehensive suite of benchmarks. So this covered things like, English and Chinese, understanding and generation, math, code, and they actually made some optimizations to those evaluation methods, both for perplexity and for those generation tasks, to better reflect the base model's true capabilities and to really improve the stability of the evaluation process, especially in those early stages. And then going a step further, they even developed a method to kind of link those evaluation results back to potential issues within the training data itself.
Interesting. So they could really pinpoint areas for improvement. So how did Ling-Lite measure up against its, open source counterparts?
So they benchmark Ling-Lite against models like Qwen 2.57b, Llama 3.18b, and Mistral 7b v0.3. And overall, Ling-Lite performed really competitively. Notably, Ling-Lite outperformed both Llama and Mistral on code and math benchmarks, and similar to Qwen, showed much stronger performance on Chinese language tasks.
And what about the larger model, Ling-Plus?
So for Ling-Plus, they compared it against models like DeepSeek v2.5, Qwen 2.572b, and Llama 3.170b. And again, its performance was comparable to the very impressive Qwen model, especially in areas like code generation, math, and Chinese. And it outperformed both DeepSeek and Llama in several areas. Now, it is worth noting that while Ling-Plus did outperform DeepSeek v2, it wasn't quite on par with that latest DeepSeek v3 model, which represents kind of further advancements.
Okay, yeah.
And then on the post-trained model evaluations, again, both Ling-Lite and Ling-Plus, they showed this, strong and comparable performance to their instruction-tuned counterparts. And both of the models particularly excelled in tool use benchmarks. One interesting finding, though, was that using few-shot prompting techniques actually had this negative impact on the performance of math tasks.
So that's interesting. Even established prompting strategies don't always work as expected.
Exactly. And then finally, they also did some evaluations focused specifically on safety, using some well-known data sets, as well as some benchmarks to assess the occurrence of false refusals.
Right.
And they found that Ling-Plus actually performed very well on those false refusal metrics, while also ensuring safety, which indicates this good balance between, being safe and being helpful.
Right, right.
And then finally, you mentioned they even tested Ling-Plus on different types of hardware.
Yeah. So it sounds like they really achieved their goal of, reducing that reliance on very specific